I wanted to address a point of confusion regarding the examples that were studied in the local bifurcation chapter of week 4. Here you see, for example, that we were studying the canonical case of a supercritical pitchfork. We found 3 fixed points, one at x equal to 0 that exists for all mu, and one at plus or minus square root of mu that exists for mu greater than 0. Then, examining the stability, I quickly wrote that x equal to 0 was stable for mu greater than 0 and mu less than 0, while x equal to plus or minus square root of mu was stable for mu greater than 0. From here, you were largely able to make the bifurcation diagram. However, when you try and check stability, you'll find that it's not as simple as what we've written. This is a point of inaccuracy in my presentation. What I meant to say was that this criterion of stable and unstable is only around mu is equal to 0. That is to say, I simply want to illustrate the stability properties around mu is equal to 0. So let's do this question properly. First, you find the fixed points by setting x equal to f of x and solving as usual. You should find the 3 points easily. Restrict the range of mu properly as we've done here for the square root of mu solutions. Second, take a derivative and check the magnitude of the gradient. Solve for fx at 0 equal to plus or minus 1. You'll find that fx equal to 1 at mu is equal to 0 and fx equal to minus 1 at mu is equal to minus 2. Checking the 3 intervals, you see that the solution is stable between mu is equal to minus 2 and mu is equal to 0. At mu is equal to minus 2, there's a period doubling bifurcation, while at mu is equal to 0, it's one of the other types. Now you know that at mu is equal to 0, the other 2 fixed points appear, and thus you already have a hint that this is a pitchfork bifurcation. Third, you check the derivatives of the other 2 fixed points, and you conclude that from mu is equal to 0 to mu is equal to 1, the solution is stable, but then undergoes a period doubling bifurcation at mu is equal to 1 because fx is equal to minus 1. So now you're ready to do the bifurcation diagram. Notice that we've drawn the arms in red of the period doubling bifurcations in a sensible way, so they should be solid where the central fixed point has gone unstable. This is largely from intuition, so we haven't proven this, but this is likely to be the case. You'll notice that I skipped the step involving the Cobweb diagrams, so now let's examine the Cobweb diagrams. Here's the old picture we had before. If you look at the function, you'll see that the local gradient is effectively 1 plus mu. So mu changes the gradient at x equal to 0, with mu is equal to 0, meaning you're lying right on top of the line y is equal to x. If mu is less than 0, but small, you have one stable fixed point, and you're slightly below the y is equal to x line at the origin. If mu is greater than 0, well, now you're above the x line, and you have 2 new fixed points. This is the pitchfork bifurcation. This was the local analysis at mu is equal to 0, but in this video we've gone further and we've done the full analysis. So let's discuss how to see the other bifurcations in terms of the Cobweb diagrams. Firstly, if mu is very, very negative, then this gradient at the origin eventually flips. Eventually, the gradient at the origin is minus 1, which means you get a period doubling bifurcation. On the other hand, if mu is large enough, then the gradient at the first and third fixed points will also pass through minus 1, which means that a period doubling bifurcation is produced. So again, the notes in this chapter only address the local bifurcation structure around mu is equal to 0 and x equal to 0, and I should have made that more clear. It's a good exercise for you to re-examine all the examples from this chapter and try to extend the bifurcation diagram.